In episode 70, titled CPE and Media Converters, Edge Realities That Break Perfect Diagrams, the goal is to focus on edge hardware as the place where ideal network designs collide with physical constraints, provider boundaries, and the kind of messy details that outage bridges are made of. Diagrams often show a clean line from your router to the provider cloud, but real sites have provider boxes, handoff types, legacy switch limitations, and small conversion devices that can quietly become the true single point of failure. The exam tests this topic because troubleshooting often hinges on understanding what you own, what the provider owns, and what pieces exist between the two that might not be visible in logical diagrams. Customer premises equipment and media converters are also common sources of misunderstandings, especially when people assume the provider is responsible for everything the circuit touches. Edge realities force you to think in terms of demarcation, physical handoffs, and operational readiness, not just routing protocols and firewall rules. When you understand these devices and boundaries, you can design redundancy more intelligently and respond to incidents faster. This episode builds the practical reasoning to interpret provider handoff problems and the controls that prevent small edge devices from breaking big architectures. Before we continue, a quick note: this audio course is a companion to the CloudNet X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Customer premises equipment, often abbreviated as CPE, is provider-supplied equipment located at the customer premises used to terminate and deliver a service circuit. The provider may install a router, a network termination device, or an optical network unit depending on service type, and that device is the provider's interface into your environment. CPE exists because the provider needs a managed point for testing, monitoring, and service delivery, and it often enforces the service parameters, such as bandwidth shaping, handoff type, and link characteristics. The exam expects you to recognize that CPE is not your core router, even if it sits in your rack, because ownership and responsibility are different. In some designs, you connect your router or firewall to the provider's CPE through an Ethernet handoff, and that handoff becomes your primary demarcation interface. The CPE may also have its own power requirements, alarms, and configuration, which can influence availability during local power events and maintenance windows. When you see CPE, you should think provider-managed boundary device that must be included in failure analysis and documentation. Understanding CPE helps you avoid blaming your network for issues that are actually in the provider domain or at the handoff itself. Media converters are devices that bridge fiber and copper or bridge speed differences, allowing two ends of a link to communicate when their physical interfaces do not match. A common case is when the provider hands off fiber, but your existing equipment expects copper Ethernet, so a converter is used to translate the physical medium. Another case is when one side supports a different speed or optics type, and conversion is used to adapt that interface to what your switch or firewall can accept. Media converters can be standalone boxes or integrated into modular transceivers, but the exam often treats them as discrete components because they introduce a new point of failure. Their behavior can also be more limited than a full switch, meaning they may not provide the same monitoring visibility or advanced features. Media converters are often introduced during upgrades, migrations, or when legacy equipment remains in service longer than planned. The key exam takeaway is that media converters solve compatibility problems, but they also add operational risk if they are not managed, powered redundantly, and stocked as spares. When you add a converter, you are inserting hardware into the critical path, and that hardware must be treated as production infrastructure. The demarcation point, often called the demarc, is the boundary where provider responsibility ends and customer responsibility begins, and it matters because outage response depends on ownership. At the demarc, the provider can test the circuit up to their equipment and their handoff, while you are responsible for everything beyond that interface, including your internal cabling, switch ports, firewall interfaces, and configurations. If you do not know where the demarc is, troubleshooting becomes a blame loop, because each side assumes the other owns the fault. The exam tests this because many outages are prolonged by confusion over whether the issue is on the provider side or inside the customer premises. Demarc also influences change control, because if a configuration change is required on provider CPE, you cannot implement it yourself without coordination. Ownership affects service level agreements as well, because providers will commit to repairing their portion but will not troubleshoot your internal network in depth. Knowing the demarc allows you to run clean tests, such as verifying link at the handoff and confirming whether the provider sees the circuit as up. When you treat demarc as a design element, you build faster incident resolution into your architecture. Documenting provider contacts, circuits, and handoff interfaces clearly is a crucial directive because edge failures are time-sensitive and often require coordinated action. Documentation should include circuit identifiers, provider contact numbers, account details needed to open tickets, and the physical location of CPE and handoffs. It should also include handoff interface types, such as whether the provider delivers copper Ethernet, single-mode fiber, or another medium, and what speed and duplex parameters are expected. Clear documentation reduces time wasted during outages because responders can quickly identify whether the issue is local or provider-related, and can provide the provider with the information needed to begin testing. The exam expects you to value documentation because it is part of operational readiness, and operational readiness is part of availability. With accurate documentation, teams may open tickets under the wrong circuit, test the wrong interface, or lose time locating the correct device in a crowded rack. Documentation also supports redundancy planning because it makes it easier to verify that two circuits are truly independent and terminate on different provider equipment. When edge details are documented, the network becomes more supportable under stress. Redundancy at the provider edge often means dual CPE or dual circuits, reducing dependency on a single provider path and preventing a single device from isolating the site. Dual circuits can be from the same provider using diverse paths, or from different providers, depending on business requirements and feasibility. Dual CPE may mean two provider termination devices supporting two circuits. Or it may mean a provider design where the CPE itself is redundant, though this varies by service type. The key is that redundancy must be real, meaning the circuits should not share the same physical conduit, upstream aggregation, or power path, because shared dependencies create correlated failures. The exam expects you to recognize that provider redundancy is often the highest leverage resilience improvement for branches and small sites, because a single circuit failure can take down everything that relies on external connectivity. Redundancy also requires your internal design to support failover, such as redundant routing decisions and firewall behavior that can switch paths quickly. Simply buying a second circuit does not guarantee resilience if failover is not tested and configured properly. When you design edge redundancy, you are creating alternate paths through provider and customer domains, and both must work. A scenario where a fiber handoff needs conversion for a legacy switch illustrates how small compatibility constraints drive real-world designs. The provider may deliver a fiber Ethernet handoff because it supports long-distance or standard service delivery, while the customer switch may have only copper uplink ports available. A media converter can bridge that gap by accepting fiber on one side and presenting copper Ethernet on the other side, allowing the legacy switch to connect. This solves the immediate problem and avoids replacing the switch immediately, which may be attractive for cost or timing reasons. The trade-off is that the converter becomes part of the critical path and must be powered, monitored, and protected from environmental issues. The exam expects you to recognize this scenario as a compatibility and operational readiness problem, not as a routing problem. It also expects you to see that the long-term solution may be upgrading equipment to accept the provider handoff directly, reducing the number of inline components. The scenario emphasizes that perfect diagrams often omit the conversion layer, yet that layer determines whether the link actually works. When you plan for conversion explicitly, you reduce surprise during deployments. A pitfall is assuming the provider manages inside wiring and switch configurations, which leads to delayed troubleshooting and unrealistic expectations during incidents. Providers generally manage their circuit up to the DMARC and may manage their CPE, but they do not manage your internal patch cords, your switch port configurations, or your firewall policies unless you have a special managed service agreement. If your internal wiring is damaged, if the wrong port is used, or if your interface settings do not match the handoff, the provider will often report that the circuit is fine, leaving you to resolve the internal issue. The exam tests this by presenting situations where a provider says the link is up, but the customer has no connectivity, and the correct reasoning is to examine the customer side of the DMARC. This includes verifying port settings, cabling, and any inline converters or patch panels. Assuming the provider owns internal issues also reduces your incentive to maintain good documentation and spares because you believe the provider will fix it. In reality, your uptime depends on your ability to troubleshoot and repair inside the premises quickly. When you understand the ownership boundary, you respond more effectively and avoid blame-driven delays. Another pitfall is letting a single media converter become a failure point without spares, because converters are often inexpensive but critical and can fail without warning. They may be powered by small external adapters, which can be knocked loose, fail, or be plugged in to the wrong power source. They may overheat in crowded racks or closets, especially if airflow is poor. They can also suffer from fiber contamination issues, connector problems, or simply hardware failure. And when they fail, the circuit appears down even though the provider side may be healthy. The exam tests this pitfall by describing a design that includes a converter and then asking what risk exists or what mitigation is needed. Keeping spares is a simple mitigation because replacement is often faster than trying to repair a converter in place. It is also important to treat converters as inventory-managed infrastructure, not as disposable gadgets, because they can take down a site. When you plan for converter failure, you reduce the chance that a small component becomes a long outage. Quick wins include keeping spares, labeling handoffs, and testing failover, because these actions directly reduce downtime and reduce confusion during incidents. Spares should include the exact converter model and any required optics or power adapters, because compatibility mismatches can waste time during replacement. Labeling handoffs means clearly identifying which port connects to the provider, which port connects to your equipment, and what the expected speed and media are. Testing failover is essential when dual circuits exist, because failover that has never been exercised is frequently broken due to routing preferences, firewall policies, or overlooked dependencies. These quick wins are valuable because they do not require major redesign, yet they address the most common outage causes at the edge, unknown ownership, missing parts, and untested redundancy. The exam often rewards this kind of pragmatic, operational control because it reflects how real incidents are resolved. When you have spares and labels, the first responder can act quickly without waiting for specialized staff. When you test failover, you convert redundancy from theory into proven behavior. An operational cue is to check link light status and to consider speed and duplex mismatches, because many handoff issues manifest at the physical interface level before any routing is involved. Link lights provide a quick indication of whether the physical layer is up, whether the media converter is passing signal, and whether the switch interface is detecting carrier. Speed mismatch can occur when one side expects a specific speed and the other side negotiates differently, leading to no link or unstable link. Duplex mismatch can cause performance degradation and errors even when the link is up, creating symptoms like slow throughput, retransmissions, and intermittent application failures. The exam tests this by describing a circuit that is up but performs poorly, and one plausible root cause is interface mismatch at the handoff or converter. Checking these basic interface characteristics is often the fastest way to separate physical layer issues from higher layer issues. It also helps you communicate with the provider, because you can report whether you see carrier at the demarc and whether the interface settings match the handoff specification. When you start with physical cues, you avoid wasting time chasing routing changes when the link itself is not stable. A useful memory anchor is demarc, ownership, handoff, conversion, redundancy, because it captures the edge elements that determine whether a circuit works in practice. Demarc reminds you to identify where provider responsibility ends and customer responsibility begins. Ownership reminds you that outage response depends on knowing who can fix which part and how quickly. Handoff reminds you that the interface type and parameters must match what your equipment expects. Conversion reminds you that media converters may be required and must be treated as critical path infrastructure with spares and power planning. Redundancy reminds you that dual circuits and dual edge paths reduce provider dependency, but only if configured and tested properly. This anchor helps you answer exam questions by forcing you to consider the physical and operational realities that diagrams hide. When you apply it, you naturally ask the right questions during troubleshooting. Where is the demarc? Who owns the failing component? What is the handoff type? Is there a converter involved? And is redundancy available and working? This structured thinking is exactly what scenario questions are trying to elicit. To diagnose an outage at the provider handoff, focus on symptoms that separate provider domain failure from customer-side failure. If you have no link light on the customer interface and no link light on the converter output, the issue may be at the physical handoff, the converter, the patch cord, or the switch port configuration. If the provider reports the circuit is up at their CPE, but you have no carrier at your interface, the fault is likely between the demarc and your equipment, such as a bad patch cord, wrong port, failed converter, or speed mismatch. If you have carrier but no connectivity beyond, the issue may be routing, authentication, or firewall policy, but you still verify that handoff parameters match the provider specification. If you have intermittent link flaps, consider converter power stability, fiber cleanliness, and interface negotiation issues, because these can cause cycling behavior. The exam expects you to reason through these layers systematically, starting with physical layer visibility and ownership boundaries. A good diagnosis also includes deciding when to call the provider, and the decision point is often whether the issue is clearly beyond the demarc. When you can describe how you isolate the demarc from the internal network, you show practical troubleshooting competence. To close episode 70, titled CPE and Media Converters, Edge Realities that Break Perfect Diagrams. The core message is that edge hardware and demarc boundaries determine how quickly you can restore service when circuits fail. CPE is provider-supplied equipment at the customer premises, and it defines the provider-managed boundary that you must understand during outages. Media converters bridge fiber and copper or speed differences, solving handoff mismatches while adding a new critical failure point that must be powered, monitored, and stocked with spares. The demarc point and ownership boundaries matter because they shape who fixes what and how quickly. And clear documentation of circuits, contacts, and handoff interfaces reduces outage duration. Redundancy through dual circuits or dual edge paths reduces provider dependency, but only when failover is configured and tested realistically. The common mistakes are assuming the provider manages internal wiring and allowing a single converter to become a hidden single point of failure without spares. Quick wins like spares, labels, failover testing, and basic physical checks such as link lights and interface mismatches turn edge incidents into manageable events. Your rehearsal assignment is a demarc documentation drill where you narrate what the handoff is, where the demarc lives, who owns each component, what spares exist, and how failover is tested, because that drill is how you turn perfect diagrams into operationally resilient networks. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.